Hello and welcome back to Tensorslow. So today we are going to make a very interesting project, a movie recommendation system. So let me give you a quick demo that what we are going to make here. So this is the Streamlit app that I have made with this movie recommendation system. So I made this app using Streamlit, and in the back end I have used my own movie recommendation model that I have made using deep learning. So this is the home page of the app, and here you can search for the movies that you want to see, and below that movie it will recommend you the similar movies like that movie. So let's say we want to watch Joker, so we will type Joker here, and it will show you all the movies with name Joker. So let's say I want to watch this movie Joker. So I will select this movie, and below this movie it will show all the similar movies with the story and character. So these are the similar movies: Batman, The Killing Joke, The Dark Knight, The Batman, Batman Begins, and let's say I want to see Bad Boys. So here I will search Bad Boys, and it will again show you all the movies with this title. So these are the movies. So now let's see, I want to see Bad Boys, and here it will show you Bad Boys, and below that it will recommend you the similar movies. So it is predicting similar movies. Here you can see Bad Boys 2, Bad Boys for Life, Rush, The Other Guys, Training Day, Cop Out, and these are the similar movies like Bad Boys. So now let's get started and see how to make this very interesting project. So in this video, I'm not gonna make the website or the web app. In this video, we will make the deep learning model that is working behind this web app. So now let's get started and see how to make it. So let me open my Google Colab notebook. So we will use Google Colab for making this project. So now let's first explore the data that we are going to use for making deep learning model. So this is a TMDB movie dataset which has 1 million records, 1 million movies dataset. So these are the columns: ID, title, and it has 24 columns and 1 million records. So now let's download this data in our Kaggle notebook, and then we will work on this data to make a deep learning project. So let me write a command to download the Kaggle dataset. So Kaggle datasets download, and here you have to download the dataset in Kaggle. You just have to write Kaggle datasets download -d, and from here you have to copy the path of the dataset. So we will copy the path of this dataset and we will paste it here, and it will start downloading. So now the dataset is downloaded. So this is the zip file. Now let's unzip it. So to unzip, you just have to write unzip and the path of this file. So it is unzipping the dataset. Now we got our CSV file. So this CSV file has 1 million record. So now let's read this CSV file and see the columns of this dataset. So import pandas as PD, and we will read this CSV file using pandas. So pd.read CSV, and here we will paste the path of our CSV file. So it will take some time because it has 1 million records. So after that, now let's see the first two records of the movie. So we will write df.head. So it is still loading the data set because this is very big data. So this is the data set. So we have 24 columns. The first column is ID. We have title, vote average, vote count, status, release date, revenue, runtime, adult, backdrop path, original title, overview, popularity, poster path, tagline, genre, production companies, production countries, spoken language, keyword. So now we are not going to use full data set. We will just use 1 lakh rows of the data set. We will only use 1 lakh records. It has 10 lakhs. So let me first extract 1 lakh. So df dot, we will easily write df dot head, and here we will pass 1 lakh rows. So now we have 1 lakh rows in this df variable. So now let's see the shape of this df. So we have 1 lakh comma 24. So we have 24 columns. Now we are not going to use all these columns for movie recommendation system. Let's first discuss the strategy, that what strategy that we are going to use for uh, making this movie recommendation system. So let me open one note here. So now let's discuss the strategy that we are going to use for making this movie recommendation system. So let's say we have a movie. Let's say we have a movie 1 and movie 2. So what are the ways to find the similarity between two movies? We will what we will do is we will generate embedding of these two movies. Let's say we have only two movies in the data set, so we will generate embedding. Let's say we have four movies in the data set, m3 and m4. So we will generate embedding of all these movies. If you don't know what are embeddings, let me first explain you what are the embeddings. So embeddings are basically n-dimensional vectors. Vector means embedding is basically n-dimensional vector representation of a word of text. So in deep learning we have this concept of word embeddings. So in this what we do is we convert words into embeddings. Let's say we have word dog, cat, and water. So dog, cat, and water. So in deep learning we will generate word embeddings of these all these words. So let's say the embedding of dog is 1 comma 0 comma 0, and the embedding of this cat is 1 comma 0.001 comma 0, and the embedding of water is 0 comma 0 comma 1.001. So let's say these are the embedding of these three words. So the embedding of dog and cat will be similar, and the embedding of dog and water will be different, which means with these embeddings we can show the relationship between two words. So basically embeddings are vector representation or the numerical representation of words of textual data. So we will convert these movies into embeddings, and then we will compare each embedding with every other embedding and find the similarity score of the movies. So let's say the embedding of this movie, let's say this movie is Bad Boys. This movie is Bad Boys, and this movie is Joker, and this movie is Bad Boys 2, and this movie is Batman. So the embedding of this movie and this movie will be more similar than the embedding of this movie and this movie, because these two movies are different. So the question is how we are going to generate these embeddings. So for that we will use this data and generate the embeddings. So now let's finalize the columns that we are going to use for generating world embeddings. So now let's see all the columns. So let me print all the columns here first. So let me print all the columns first. So df dot to list. Let me print this. So these are the columns that we have in our data. So we are not going to use all these columns for generating embeddings. So let me show you here. In ID we have movie ID. So this is not of our use. So let me first clarify here. We are only going to use textual columns with text, and we will remove all the columns with numerical value. So first we will remove this column because it has numerical value. Then the second column is title. So title can be useful because some movies have franchise like Bad Boys and Bad Boys 2, so it will give you a more similarity score than other movies. So we will keep this column title. Vote average, it is numerical column. Vote count is a numerical column. Status, released and unreleased. I don't think status released and unreleased movie will change your mind for recommending movies. So we will not going to use this column also. Then we have release date. Obviously, it is a numerical column. Revenue is a numerical column. Runtime is a numerical column. Adult. I don't think this is a good option for recommending movies, because all the movies are 18 plus, and so many movies are 18 plus, so the data can be biased. So we will not use this column also. Then we have a backdrop path. We will not use this. So first column that we have chosen is title. So let me write here. We will use title. So the first column that we have choose is title. We have removed this column. Budget is not a proper way to recommend movie because budget can be different according to the location, and but the story can be similar. So homepage, IMDb ID, these two are not useful. Original language, original title we have already chosen here. Overview can be useful because let's see what is in this column, overview. So let me see the original data. So overview column, yeah, this is the overview column. So it is giving the short description of a movie. So this will be a useful column. So we will choose this column also. So we have title and then we have overview, and after that popularity is I don't think popularity of a movie depend on the story of a movie. Poster path, tagline. Poster path is also not useful. It is path of the poster. Taglines can be useful. uh, Let me see what is in the tagline. Your mind is the scene of the crime. So yeah, tagline can be useful. So we will select this column also. So tagline. Then we have genre. So action science. So this can be a useful column. So we will use this also. And then we have production companies, production countries, spoken language, and keywords. So keywords again, I think it is a useful column because it has all these keywords that are defining the story of a movie. So we will use keywords also. So now we got our title, all these columns. So we are going to use these columns for generating embeddings. So we have one, two, three, four columns: title, overview, tagline, uh, genres, and keywords. We have five columns that we are going to use to generate word embeddings. So now let's take these columns and store them in a different place. So we are what we will do is we will create a new column, in the dataset called tags. So and for tags we will use tf dot title. So we will use title, and so let me first explain you what I'm doing here. So we will generate tags. So what does it mean? So we will take title. Let's say title is Joker. So we will take Joker, and we will concatenate all these columns. We will concatenate all these columns and generate uh, a new column called tags for all the movies. So we will take title, overview, tagline, genre, and keywords, and we will concatenate all these columns and generate a new column called tags and store all the tags of movies in this column. So let me write this. So then we will df dot keywords, uh, keywords. So I have generated a new column called tags in this data set. So now let's see the shape of our data frame. So we have 25 columns uh, because we have generated a new column called tags. So if you will see this column, tags, uh, so it will show you these text. So now let me print the first column. So Inception, this is title, and this is overview of a movie, and we have concatenated all the words, all the text in one word, and this is the list. This is the string, and we have generated this for every movie in the dataset. So now this is done. And so now we have to generate word embeddings. So let me show you what I'm talking about. So we will use a transformer, a sentence transformer to generate word embedding. So we will use a pre-trained transformer to generate word embeddings from these tags. So what we will do is we will use this transformer, let's say this model, and we will pass all these tags in this model, and it will generate the word embeddings of this column tags. So now let me import this transformer here. So we have to import, so let's also import numpys, and from sentence transformers import sentence transformer, and we will also need cosine similarity for to calculate the similarity score, and we will do one more thing, which is from sklearn dot decomposition import PCA, and we will also import, so this is enough, so let me run this cell. Okay, so we have imported all the necessary libraries. So now let's discuss the plan of action. So now we have generated the tags, and now we have to convert these tags into word embeddings. So we will pass these tags in our model, pre-trained transformer model, and it will give us the embedding. So we have to define the dimension of embedding. So this transformer model, this pre-trained transformer model, generate the embedding of 384 dimensions, 384 dimensional embeddings. But this could be very hectic and memory draining task to store 348 dimensional embeddings. So we will use PCA. PCA is a dimensionality reduction technique. So we will use PCA to reduce this dimension into 100 dimensional vector or embeddings. Why we are doing this? We are doing this to save memory, and time. So calculating the similarity of 100 dimensional vector will be less memory draining and time taking than calculating that of 384 dimensional embedding. So now let's get started, and so first we will create the object of this sentence transformer. So we will use this npnet base v2. We will use this model, this transformer model. So this is getting downloaded. It will take some time. So now we have downloaded this transformer model in our notebook, and we are ready to use this. So first, so now we have to remove, as you can see, here are some dash, and it might contain some numerical data or some numbers. So we will remove those special characters and number from this column tags. So to do that, we will use a regular expression. So import RE, and we will create a function def. So it is giving me the recommendation. So what this function will do is, this function will only select the alphanumeric characters, which means it will remove all the special characters from the tags. So let me run this, and here we will pass our tags. So tags equal to df.tags apply clean text. So this function will get applied to this tags column, and we will again store this in tag. So let me run this. So it is saying expected strings byte like object got float. So it has some float in between. So we will convert this into string. So convert s type, and now let's again run this code. So yeah, it is working. Now let's generate the embeddings. So we will store embeddings in this variable. So to generate embedding, we just have to write model dot encode, and here we have to pass our tags. So we will write df.tags, and we will convert this into list. So to list, and here we will pass one more thing, which is show progress bar equal to true. So this will show the progress bar while generating the embedding. So here we are generating the word embeddings of these tags columns, and we are storing those embeddings in this embedding variable. So this will take time because we have 1 lakh columns and we are generating 384 dimensional word embeddings. So just wait. So it is taking longer than usual. uh, I am running this on CPU, so if you are running this task, so change this into GPU, and then it will compute all the embeddings faster. So let me restart this session and calculate the embeddings. Now I was running this code on CPU, but all this is a deep learning task, so it requires GPU because it is doing too much computation. So make sure to turn on the GPU from here, and if you have a machine with GPU, so make sure the GPU is running. So I've restarted this session and running all the cells again. So this time this will work faster because now it is running on GPU. So let's wait and watch. So yeah, it is running faster than before. So wait until it generates all the embeddings for these tags. So it is completed. We have generated all the embeddings for all the tags. So now if you will see the embeddings, the shape of embeddings, they will show you. So I have reduced this data. And now I am using only 20,000 records from the data because it was taking too much time. You can use 1 lakh or you can use full data if you have powerful machine. So I've used 20,000 records from the data. So we have generated 20,000 word embeddings of 768 dimensional word embeddings of 20,000 record. So now we have to reduce the dimension. So to reduce the dimension, we just have to create the object of PCA class, and here we have to pass n component equal to 100, which means now we are reducing the dimension of these embeddings to 100 dimension. So we will write reduced embeddings equal to PCA dot fit transform, PCA dot fit transform, and here we will pass the embeddings. So it will reduce the dimension of embeddings, and now if you will check the shape of this reduced embedding, so we have 20,000 records and every record has 100 dimensional word embedding. So now let's store these embeddings in the column. So df dot embeddings. So we have created a new column. So now if we will check the shape of here, it will show 26. So initially we have 24 column. We had 24 columns. Then we have generated one more column called tags, and now we have generated one more column called embedding. So now let's select the useful columns from the data. So df, and here we will pass the useful columns. So we will select poster path, which is useful for us. We will use them in making app, and we have title, and we will select embeddings. We will not select this release date column. So we have title, we have embeddings, and we have poster path. So now if we will check the shape, it is 20,000 comma 3. So we have selected useful columns of this data frame. So now let's see. So we have generated the embeddings. Now it's time to make prediction and see how this is working. So this is the function. This is the function for movie recommendation. So now let me try this. So recommend, and here we will pass our movie. So let's say Bad Boys. So yeah, it is recommending Bad Boys 2, Bad Boys for Life, Rush, The Other Guy, Training Day. So our model is working perfectly. So now let's take a quick recap that how this model is working and what we did for generating the movie recommendation model, for making movie recommendation model. So initially we had data, TMDB data, TMDB data with 1 million records. So first we have selected 20,000 records because we have limited memory. So we have selected 20,000 records from the data, and we have selected 5 columns, 5 useful columns for movie recommendation. And these were the columns that we have selected: title, overview, tagline, uh, genre, and keywords. We have selected these 5 columns and we concatenated them and created a new column called tags. So we have concatenated all these 5 columns, and then we have generated the embeddings of these tags from these tags with pre-trained transformer model. And these embeddings were of 784 dimensional, I think. These were 784 dimensional embeddings. So then we used PCA to reduce this dimension to 100, because this will take more space and time complexity. So we have reduced the dimension of these embeddings to 100 dimensional embeddings. So now let me explain this function, that how this function is working. So this function is working. We are passing the title of a movie. We are passing the title of a movie. So this function is searching that title in the data set. So this will search the title in the data set, and when this will find the title, so it will take that record. It will take that record, which means let's say we have searched for bad boys. So it will search bad boys in the title column of the data set, and then it will take that record, that row of a bad boys column, and from that row it will extract this column called embeddings. So it will take this column called embeddings. Then this embedding column, this embedding column, this embedding column contains the word embedding of this bad boy tags, bad boy movie tags. So it is the 100 dimensional vector, and then it will search for the similar movies, which means it will compare this embedding with all the other embeddings. So let me show you how this is working. So how it is, it can tell that these two embeddings are similar. So for that we will use cosine similarity. Cosine similarity. So what cosine similarity does, let's say we have a 2D space. This is the 2D space, and this is the vector of bad boys, and this is the vector of Joker movie, and this is the vector of Bad Boys 2, and this is the vector of Batman movie. So it will this cosine similarity will calculate the this 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 distance between two vectors. So this cosine similarity will go through all the records of our data set and compare this embedding of bad boy with all the other word embeddings in the data set, with all the other word embeddings in the data set in real time. We are not storing these similarity score anywhere, because that will be more computationally expensive and it will take more space. So we are trying to save time and space here. So we will calculate that in real time. So when we will pass the title in the function, it will first search for the movie and it will extract that row from the data set and extract embedding of that movie. And then it will calculate the cosine similarity between all the word embeddings with this word embedding. So cosine similarity is between, basically this distance. So as you can see that this distance between these two movies and the distance between this and the Joker movie is more. So these two this depicts that these two movies are more similar than these two movies. So uh, then it will select the maximum similarity score movies and top 5 maximum similarity score movies. So this is how this movie recommendation system is working. Now we have to save the model. So to save the model, what we will do is we will simply write model dot, we will import pickle, and using this we will download this. So what we need to recommend movies, we need this column embedding. So embedding, and for searching we need this column called title. So we will save this in pickle. So df dot to pickle, and we will save this with movie embeddings dot etl. now we have saved this .pkl file. So this pkl file has, if you want to read this, so you can read this using pd.read pickle movies embedding.pickle. So this will show you all these columns. So we have stored all these all this data, and with the embeddings of a movie. So we can easily recommend movies using these embeddings. So this is the video, guys. In this video, we have learned that how to clean the data and generate word embedding using pre-trained transformers, and we have made a movie recommendation system using deep learning approach. So in next video, we will use this pre-trained model, this saved model, to convert it into a fully functioning Streamlit app. So that's it for the video, guys. Thank you for watching, and make sure to like and subscribe if you found this video useful.